Hi everyone. So let's get started. All right. So this is what we have. What I have planned for um, the next few weeks until the final. Okay. So again, homework 10 will be due tomorrow, but I have actually homework 11 available online already. You guys can work on that if you finish 10. Okay. It's going to be due next Tuesday, and then the last homework will be due Monday, the last week. We are going to take the exam, the final exam on the Wednesday, which is scheduled to be the last lecture. Okay, so we'll be having our final exam on that date. Okay, it looks like we are going to be finish the lecture ahead of time by 2 or 3 lectures. So we will have our final exam on the last day. Okay, so that's why I have for the um, reminder of the weeks throughout the semester for right now. Okay. And final exam will be covering the content in homework from 10 through 12, or from chapter 11 through, I think, 15, chapter 15. Okay. All right. So let's again take a quick look on what we mentioned last time, or what we learned last time. So last time we give a definition for fluid. So basically anything that is liquid or gas, we consider them as fluid. Okay. And we also briefly mentioned about the definition for density. So density should be equal to mass divided by the volume. Okay. And then density could be localized. So that means at a particular local point, your density may be varying from other locations. Okay. Then you just take a small delta m divided by delta v at that small location, take the limit of delta v go to 0. That will give you the local density. Another term related to density is called specific gravity. So it's a unitless quantity. It's the density of the material divided by density of water at 4 degrees Celsius and under the normal 1 atmosphere pressure. Okay, so just keep in mind that when we talk about density, it has to be actually specified, like at what temperature and then under what pressure. Okay. So those 2 conditions also has to be specified. But otherwise, if not specified, then we're talking about a normal condition, like what we usually have in our room condition, that is assuming to be having 1 atmosphere and room temperature. Okay. All right. And we also took a look definition of pressure as equal to force divided by area. Now, force can be, or pressure can be also localized. So at different location, you might experience different pressure. Then you'll be doing derivative of F divided by derivative of area. Okay. In the inside a fluid, the pressure varies as locations, or in the vertical height over here, due to the weight of the different parts of the fluid. Okay, that is exerting on the lower part of the fluid. So then dp over dy is equal to minus g times rho. Okay, and that will give you the pressure in the fluid with a constant density, assuming density doesn't change too much. So then pressure inside the fluid equals to pressure on the top of the fluid, the surface of the fluid, plus rho gh. Okay, so that's pressure inside fluid. In air, or under the in the atmosphere here on Earth, on the surface of Earth, then pressure is given by the weight of the air divided by the area at the bottom here. Okay, so and the pressure of air actually decreases as the altitude increases. Okay, so if you go up the hill, then or the mountain, a very high mountain, you'll expect that pressure will decrease at the top of the mountain. Okay. All right. Now pressure inside fluid actually acts on all directions, or we can say no directions. Okay. So then we can treat pressure as a scalar quantity. The device we use to measure pressure, usually called pressure gauge, that actually measures the relative pressure instead of absolute pressure. So if you want to solve for the, or calculate for the absolute pressure, then you do P from the gauge plus P atm, okay, the atmosphere pressure. All right, in chemistry, it's often pressure is often measured by a barometer. So a device like this, we actually have one mercury barometer in the lab. Okay, so you guys will use that next semester in physics too. All right, but again, it's because mercury is the fluid, so then pressure is equal to rho gh or h rho g. Okay, in the same sense. We also mentioned about Pascal's principle and hydraulics. So basically, pressure inside the fluid acts in all directions, and then it's uniform in all directions. So then if you have a change on one side, then on the other, all other sides or all other locations inside the fluid, you should have the same change in pressure, okay? So in that sense, you can design a hydraulic device like this. So you can apply small force, the result will be a relative larger output force, okay? So that's what we learned last time. So today we are going to just keep checking on this a couple more sections in this chapter. So the first thing we'll be looking at is called Archimedes' principle and buoyancies. Okay, so we know that boats usually float in the water, and then we know that heavier object, for example, metal, actually will sink down to the water. All right, and similarly in the air, if you have balloon that is filled with helium, then balloon can be floating in the air as well. Okay, so all these objects are experience buoyancy forces, okay, which is an upward force, all right, in the opposite direction of the gravity. So the origin of the buoyancy force is because when an object is merged into either partially or fully merged into a fluid, so then the pressure inside the fluid varies by depending on the height that you are in the fluid, right? So for example, if you have a cylindrical object here, as the figure shows here, inside the fluid, then because pressure at the top is less than the pressure at the bottom, so then the force that the bottom experience is, if the bottom has the same area as the top, then will be a larger force than the top experience. Okay, so there's a difference in these two forces, F1 and F2. The net result is the buoyancy force. So F2 it will be minus F1 will be the buoyancy force that is going to be in the upward direction. Okay, so that's buoyancy force. We use F sub B for that. All right. So, so then any object inside the fluid should also experience buoyancy in that sense. Okay, now you may be having an irregular shaped object, but then, so on, let's say, the half top part of the object and then the half bottom of the object, right? You can have the forces differences. Okay, so then that will give you buoyancy force. And the buoyancy force, the originally was discovered by Archimedes. So I think you guys might have heard the story. So the king at that time actually had a crown made by someone, and then he suspected that the crown was not made of pure gold. Okay, so then he asked the wise man at that time, Archimedes, to determine if the crown is made of the pure gold or not. Okay, but Archimedes didn't have the idea initially himself either. So he has been thinking about that all the time. So one day he was taking bath, and as his body merged into the water, then water come out of the bath. So then he got the idea that you can actually use buoyancy force to kind of so he has this idea that the buoyancy force is acting on the object is equal to the weight of the fluid displaced. Okay, so that's the principle he's discovered, and then he can apply that to determine what's the density of the crown. So then according to the density, he can see if it's pure gold or not. Okay, so we'll see about that in a couple of slides. Okay, but basically buoyancy force equals to weight of the fluid being displaced. Okay, so for example, if you are swimming underwater, then the buoyant force the water exert on your body should be equal to the weight of the fluid, the water being displaced by your body. Okay, so then this amount of the water, the weight will be equal to your buoyant force acting on you. Okay. So then let's see how you can actually determine density by applying Archimedes' principle. So if you have an object in the water, okay, then the weight of the object you can actually write down as mass of the object times g, right? Which is equal to the density of the object times the volume times g, okay? And for the fluid displaced by the object, that is equal to the mass of the fluid times g, right? Which is equal to the rho of the fluid times volume times g, right? So then, according to Archimedes' principle, so then the buoyant force should be equal to the weight of the fluid displaced, okay? So if you put an object into the water of any other kind of fluid, right? So then you can see, let me see over here. So then if an object is floating, then these two should be equal to each other, okay? So rho object is not equal to that guy. If not, so depending on the density of the object, so it could be having like the density that is larger than the fluid or smaller than the fluid. So basically for a boat itself, okay, so then the density of the boat overall should be less than the fluid, right? So then it's floating. So you can actually look at the volume of the object and then look at the volume of the portion that is being submerged, okay? So volume being submerged divided by volume of object is called, this is defined as fraction submerged. And the volume of the subject of the part that is submerged is equal to the volume of the fluid being displaced, right? So then the volume of the fluid being displaced should be equal to the mass of the fluid being displaced divided by the density of it, right? And then for the volume of the object, it should be equal to the mass of the object divided by the density of the object, right? Because density equal to mass divided by V, okay? So in that sense, all right, so then according to Archimedes' principle, because buoyant force equals to m fluid times g, right? And then the weight of the object is also equal to mass of the object times g. So then if this is floating over there, that means it's not sinking down, right? So then the buoyant force and the weight of the object should equal to each other. So then the mass of the fluid displaced should be equal to the mass of the object, all right? So then fraction submerged should be equal to actually the density of the object divided by the density of the fluid, okay? So if you have an object that's having a certain density, all right, you can determine, so by this equation, the equation in red, you can tell if the object is going to be floating in the fluid or it's going to be sinking down, right? So if the density of the object is less than the density of the fluid, then it's going to be floating because then the fraction that's submerged would be less than 1, right? So then that means it will be just part of it will be in the water. If the object has heavier, larger density than the fluid, then the object will be sinking down, right? Because then the portion that is submerged will be greater than 1. That means it's going down, okay? All right. So we'll take a quick look on this example here. I think we can take a look on this together because it's a rather simple one. So this one says if your body has a density of 995 kilograms per meters cube, what fraction of you will be submerged when floating gently in fresh water? Okay, so fraction submerged All right, that will be equal to rho of the object divided by rho of the fluid, right? So then your body is having 995 kilograms meters cube density. The water is 1,000 kilogram density for fresh water. Okay, so then 0.995 in that fraction, okay, will be submerged in the fresh water. Okay, on the second part, then fraction submerged should be equal to, again, the object density divided by the fluid density. So in this case, 995 be again your density, and then divide by this salt water, which is 1027. Okay, that would be equal to, let me see my note here. So it's going to be a little bit less than the previous one, but still 0.969, okay? That's how much will be submerged into water, okay? All right, now let's get to the real part, that how you can actually determine the density of, so for example, if you were Archimedes, then this is how you are going to do, right? You are going to wave the crown when it's in air, all right? And then you are going to put into water, all right? And then take this measurement again for the weight. So this time you are having apparent weight, right? Because it's not a real weight, it's the weight in water, all right? So by doing these two measurements, let's see how you can actually figure out what's the density of the object, okay? So in this case, if you look at the specific gravity, that means the density of the object divided by the density of the water, right? Then if you multiply both numerator and denominator by g times v, so then this is what you get. Rho gv, v will be the volume of the object, and then g is the gravity, right? So then equal to mg, the mass, times g, which would be the weight, all right? And then divided by mass of the water times g, okay? Which is equal to the weight of the fluid being displaced, right? So then for buoyant force on the object, right? So this is the water here, all right? So then when you, this is a real mg, now buoyant force should be acting upward, right? And then the difference of these two will be what you are reading from the balance, right? The apparent weight. So then W apparent would be, this guy would be equal to mg minus fb, okay? So fb is the mH2O(G), right? It's the weight of the water being displaced, all right? So then mH2O(G) is equal to this guy, which is the weight, right? The real weight minus WAPP, okay? So which, as this equation says, all right? So then you can see your specific gravity will be equal to your real weight divided by the real weight minus the apparent weight, okay? So this will give you the specific gravity, all right? Then from there on, you can calculate what's the real density of the object, okay? So let's take a look on this example here. This one says a rock with a mass of 540 grams in air. So this is the real mass. It's found to have an apparent mass. Okay, so that means the mass when it's submerged into water. So that's 342 grams. Now, one mass of the water is displaced, and then what's the volume of the rock? What's its average density? Okay, so three things you want to calculate it. So I will give you guys a few minutes. You can work on this, and then we can take a look at the solution in a couple of minutes later together. All right, so let's take a look here together, okay? I think I see a few responses in already. So similarly here to this what I sketched earlier, okay? So the object, the rock, if you assume this is a rock inside the water, so then when you are measuring the apparent mass, it's going to be just whatever the mass of the rock minus the mass of the water being displaced, right? Which is equivalent to the force, buoyancy force here divided by G, right? So then in this case, in A here, because MH2OG is equal to the weight, real weight, mg of the rock minus m apparent of the rock, right? This is the apparent weight. This is the real weight. That will give you the weight for the water being displaced by the rock, okay? Because that's because MH2OG is equal to the buoyancy force. And then from that free body diagram, you can see this equation, okay? So you're looking for m of water displaced, you can see the G will just cancel out. So basically, then the mass of the water being displaced should be equal to the difference of the real mass divided by the apparent weight, okay? So MH2O is going to be equal to m minus MAPP, 540 grams minus 342 grams. Okay, that will give you 198 grams for the mass of the water being displayed. Okay. The second one is asking what's the volume of the rock. Okay, so the volume of the rock should be equal to the volume of the water being displayed, right? So those are the same because because the volume of rock will take the place of the water being displaced. So then, this is how much the water being displaced according to rho equals to m divided by v. So then if you are looking for volume of the water being displaced, that should be equal to the volume of the rock, right? Then that should be equal to mass of the water being displaced divided by the density of the water, okay? So we are going to just use the density for the water as 1 grams per centimeter cube. So in this case, 198 grams divided by 1 grams per centimeter cube, right? So that gives you 198 centimeter cube for the volume of the rock, okay? The last one is asking you what's the density of the rock. So the density of the rock then would be equal to the mass of the rock divided by the volume of the rock, right? So mass is equal to 540 grams divided by 198 centimeter cube. That's 2.73 grams centimeter cube, okay? So you can use the CGS unit here, or if you want to use the SI unit, then you'll be doing kilograms times meters cube, okay? So so let me see, yeah. So I think all your responses are correct, okay? So good job on that one. All right, let me know if you have questions on this one.
What was the apparent weight again?
So the apparent weight is the weight when you are measuring the object in the fluid. So in this case, it will be equal to the apparent mass times G, okay? Because when you are measuring the weight of the object in air, that's the actual weight, right? And then when you are measuring it in water, it will be different. That's called the apparent weight, okay? Now this apparent weight is different is because there's buoyancy force on the object, okay? So you take the buoyancy force out of the actual weight. All right.
Thank you. That makes a lot more sense now.
All right. All right, so next we are going to take a look at the dynamics of the fluid, okay? So when the fluid is floating, actually, there's two types of flows of fluid, okay? So one is called laminar flow. So then basically it just flow the fluid for a particular, if you look at a particular molecule of the fluid, it will just go in one direction, okay? Now, there's also a second type of flow. It's called turbulent flow. So then it actually goes like goes backward. Okay. Although for the fluid itself, maybe for the as a um, like a big object or unity, it's going in one direction, but inside there will be like this small flows called turbulence flows. Okay. So those are the two types of flows. Okay. All right. So let's take a look if the fluid is just going in one direction, okay? So then what happens is here is so you can see if you take a part of the fluid here, so you can see it's going through a channel over here, all right? So basically, if there's variation in the cross-sectional area of the channel over here, all right, then the same time period, this guy, if it goes through one particular point over here, all right, so let's say take this cross-sectional area over here. So the amount of fluid going through this cross-sectional area should be equal to the amount of fluid that is going through a different point. So say pick a different point over here, then same amount of fluid will go through that cross-sectional area, okay? So this is called the flow rate over here. So if you do volume of the fluid divided by the time t, that's called flow rate, okay? So flow rate at one point should be the same as at the second point, okay? All right. Just for right now, let's just focus on the quantity flow rate. It's change in volume divided with change in time t, okay? And then change in volume can be calculated as cross-sectional area times the length it traveled. Okay, if the cross-sectional area doesn't change, then it's the area times dx over dt, which it will give you the speed of the flow. Okay, so then area times the speed is also equal to flow rate. Okay, so now pay attention to the when it says flow rate is defined as the volume divided by time t. All right, it can be equal to area times velocity or speed. The SI unit for flow rate is meters cubed per second, okay, because it's volume divided by time t. All right. So as I mentioned, at one point compared to another point in the flow, the same amount of water should go through a particular location and then at a different location, right? This is called the continuity of flow. So the same amount of water, so for example, in upstream here enters from the upper stream should be equal to the same amount of water coming out of the lower stream over here, okay? So this is called continuity of flow. And happens also when you have a change in cross-sectional area of the pipe. Okay, so if flow of water, say water goes through here, then it has to come out at a different point later on. If the cross-sectional areas are different, so then A1 V1 is equal to A2 V2, okay, because the same amount comes in should be equal to the same amount comes out. Okay, so basically you are going to do like A1 times X, right? The amount would be equal to A1 V1 times T. So basically this is A1 V1 times T equals to A2 V2 times T. The T will cancel out. So then the formula for continuity of flow just reduced to A1 V1 equals to A2 V2. Okay, in this case, A is the cross-sectional area, V is the speed at different locations. Okay, so if you have a larger cross-sectional area or larger area here, then the flow rate will be smaller than if you have a smaller cross-sectional area over there. Okay, so V2 will be larger at that point when A2 is small. All right, let's take a look on one example here. It says the Hookah Falls on the Waikato River is one of the New Zealand's most visited natural tourism attractions. On average, the river has a flow rate about 300,000 liters per second. At the gorge, the river narrows to 20 meters wide and average 20 meters deep. What's the average speed of the river in the gorge? And then what's the average speed of the water in the river downstream of the falls when it widens to 60 by 40? Okay. So flow rate, I think we use Q, that's equal to A times V, the area times the speed. Okay, so I think that's the equation you want to use. And then also according to continuity of the flow, A1 V1 will be equal to A2 V2. Okay. So again, I'll have you guys work on this and then we can take a look at the solutions together just in a couple minutes here. All right, let's take a look on this one together. Okay, so you're basically going to apply this equation and that one if you want. Okay, um, so it tells you the flow rate. Okay, and then tells you the dimensions at one location. So then we are looking for speed. The flow should be equal to flow rate divided by the cross-sectional area. Okay, so this is 300,000 liters per second divided by the area of at the first location 20 meters times 20 meters. Okay. You want to be careful about units here. So this is given in liters. All right. So you probably want to convert it into meters cube first. 1 meters cube is equal to 1,000 liters. Okay. So that would be 300 meters cube per second divided by 20 meters by 20 meters. Okay. So then this will give you 0.75 meters per second. All right. You can use the same equation for the second part. You just change the area, okay? So this is V1, A1. Then V2 would be equal to Q, the same Q divided by A2. Again, 300 meters cubed per second divided by, in this case, it's widened to 60 meters by 40 meters, or 40 meters by 60 meters, okay? So then it's equal to 0.125 meters per second, all right? You can also use that equation if you want on this part, okay? So the same result you'll get, okay? All right. Let me know if you have any questions. All right. So if not, then let's again let's recheck on the continuity of flow. So it's basically mass conservation. Okay, so that the amount of water goes comes through one point should be equal to amount of water comes at the second point. Okay, so that's basically conservation of the mass. The mass doesn't change, right? So if you look at that from the point of mass. Look at that from the point of mass, then mass equal to V times rho times volume, which is equal to rho times cross-sectional area times X, all right? So dm over dt, the change in the mass should be the same at one location compared to another location, right? So dm over dt then will be derivative of rho times A times X. If location doesn't change, if the cross-sectional area doesn't change and then rho doesn't change. So then it'll be just equal to rho times A times dx dt. dx dt will be the speed, all right? So then rho times AV, all right? So at one location, now this is assuming if A is not changing, right? Now A could be changing. So at the end over here, if you are at one point, then this dm dt is equal to rho A times V, and the second location will be equal to, at location 1 will be rho 1 A1 V1, right? At location 2 will be rho 2 A2 V2 as indicated here. Now the density is probably not changing. So then the density can cancel out, rho 1 and rho 2 cancels out. So then the continuous flow equation becomes this guy, right? A1 V1 equals to A2 V2, okay? All right, so that's that one. That section. Now let's take on the next section in the textbook here, Bernoulli's equation. All right. So if we are looking at one part over here, all right. So if this is a larger cross-sectional area, this is smaller cross-sectional area. Okay. So you can see a larger cross-sectional area, V1 is smaller, V2 over here is larger. So when this amount of water in the shaded volume here moves to the second location over here, you can see the velocity or the speed changes, right? The speed increases in that sense. So then let's network them to the this volume of the water, right? So network is equal to the kinetic energy change. All right. So then let's take a look here. So if you are looking at one location, so on the previous figure, the two locations are at the same height. Now, in reality, the two locations might not be at the same height, right? It could be like in this place and then at second place, Y1 here, Y2 here. So in this case, you can see from position 1 and position 2, all right? So then there's change in kinetic energy and also change in potential energy. That would be equal to change in the work, okay? Or the net work should be equal to change in kinetic energy plus change in potential energy, all right? So in the figure shows here, you can see there's force applying on this side, all right? Now at the same time, there's force applying on that side, all right? So then the net change in work should be equal to F1 times dx1 minus F2 times dx2, all right? And then F1 will be equal to P1 times A1, F2 will be equal to P2 times A2, okay? So A1 times dx1 then will be the volume change, dV, all right? And then A2 times dx2 will be the volume change as well. So you can see this is due to the pressure difference at the two ends of this channel over here. So the pressure difference times the change in volume, all right? That equals to the change in work. Now let's look at change in kinetic energy. Should be equal to 1/2 m2 v2 squared minus 1/2 m1 v1 squared, okay? So for the mass, it's the same mass, it's the same rho times dv. So then it will be just v2 squared minus v1 squared. You can single out the mass, okay? Now change in potential energy would be mg y2 minus mg y1. Again, the mass is the same mass, so rho dv, okay, that's the mass times g times y2 minus y1. We will take those three expressions into this equation on the top here, okay? Expression for dw, expression for dk, and then expression for du. All right, so then this is what we got. So then P1 minus P2 dV equals to 1/2 rho dV velocity. The lowercase v stands for velocity. V2 squared minus V1 squared plus rho dV g y2 minus y1, okay? dV is the same dV across, so that cancels out. So then you have P1 minus P2 equals to 1/2 rho V2 squared minus V1 squared plus rho g y2 minus y1, okay? So, and if you rearrange the terms, okay, everything denote as 1 to one side of the equation, and then the rest denote as 2 to the other side of the equation. So you arrive at this expression here called Bernoulli's equation. So P1 plus 1/2 rho V1 square plus rho G Y1 equals to P2 plus 1/2 rho V2 square plus rho G Y2, okay? So initial equal to final, or you can say it's constant, it's not changing, right? So then P plus 1/2 rho V squared plus rho G Y is equal to constant, okay? So that's basically Bernoulli's equation. All right, let's take at different scenarios, okay? So if the fluid is in a static situation, then we are having static fluid and it's not moving. So then velocity equals to 0. Y1, Y2, they are both equal to 0, okay? So then for the Bernoulli's equation, let me write on my paper, we can refer to that. So it's P1 plus 1/2 rho V1 squared plus rho GH1 equals to P2 plus 1/2 rho V2 squared plus rho GH1, okay? In a static liquid fluid situation, you have this term and this term as 0. So then Bernoulli's equation reduced to 2 terms on each side of equation, all right? And if the two locations are the same height, H1 and equal to H2, right? So then this term will cancel out this term. Rho GH1 will cancel out rho GH2. Actually, it's rho GH2 on the right-hand side here. So then again, Bernoulli's equation reduces to 2 terms on each side of equation, this one and this one, okay? So then on the left hand side, you have P1 plus 1/2 rho V1. On the left hand, the other hand side, the right, you have P2 plus 1/2 rho V2. Okay, and this is called, if the height is the same, it's called the Bernoulli's principle. Okay. All right. Now let's take a look some applications of Bernoulli's principle. Okay, so you might be wondering how the airplane, it's such a heavy object, can be flying in the air. Okay, so this is because the design of the wings, here on the top of wing is curved. Okay, on the bottom of wing is straight. So then for the air going through the top of the wing, the path is longer. Then the air passes through the bottom of the wing. Okay, so that means for the velocity on the top of the wing for the air here, its v is larger. Okay, and then at the bottom here, v is smaller. Okay, so according to Bernoulli's principle, so this term, the high term, goes away. Okay, so if you have larger velocity and then you squared it, all right, and then plus P1, that is going to be equal to a smaller velocity plus P2. So then P2 has to be larger than P1 in order for the equation to be satisfied, okay, to equal to, from like both sides equal to each other. So in that sense, you can see pressure underneath the wing will be larger than the pressure on the top of the wing. So then there's a net force, okay, from the bottom minus the top. Okay, so that provides the lift for the wing here, and then also happens to the other side. Okay, so I think you guys are going to get a practice problem in the homework assignment on this guy. Okay, to calculate how much force actually will produce for the airplane when it's flying. Okay, but that's the principle there. Other applications, okay, so like in your household, okay, you can see that so when natural gas is floating, okay, so there's an opening over here, it will also take in the air, because if this is floating here, so then the flow inside this channel will have a relative larger speed, right? So then the pressure inside here will be smaller than the pressure outside here, so then the air will be pushed in. Okay, so you don't have to actually have another like supply channel for the air to come in. Just open up, have an opening here, then air will be pushed in. Okay, now also if you have a perfume bottle, if you want to kind of smell it, you kind of you can give some air on the top over here. So then there's a velocity for the the air molecule here. Then the pressure here will be smaller. Then the perfume will be pushed out. Okay, so because of the pressure difference. Okay, also if you go to dentist, so then there's a tube coming into your mouth sucking some waters out, right? So that's also because of the there's water running through, and then this guy can be somewhere producing lower pressure inside here, and then outside pressure will be larger. So then it actually can take in air or whatever liquid maybe will be pushed by the pressure difference inside here. Okay. For the chimney here as well, so if you are burning some hot air, so hot air will go out the chimney here, then cold air will be picked in here because the air pressure here is smaller than the pressure outside the chimney. Okay, so you can just do that as well. All right. So I wanted to take a look on this example, but it looks like we are almost out of time. So I probably will save this for the next lecture, okay? So next time we'll start from the example here, okay? So let me just stop here for today, okay? And then when we come back to class tomorrow, we'll check on this, okay? So I will see you guys tomorrow.